today what we're going to do is we're going to talk about postulates in paragraph groups. And so a postulate is also called an axiom, and it's a rule basically. It is a statement that describes a fundamental relationship between the basic terms of geometry. It's just a rule. It's accepted true without proof. Now we're also going to talk about theorems, and a theorem is also a rule, but it is backed up with proof. All right. This one is just kind of a common sense rule between the basic terms of geometry. And so we're going to go through these postulates. I'm going to explain what they mean. Some of them will seem like they're saying the same thing, but it's not really, and I'll try to explain that to you. Okay. And we've already talked about a lot of these, but we're just actually naming them as postulates. And the first one is, through any 2 points, there is exactly one line. So what that means is that if you have this point A and you have this point B, exactly one line can be drawn through those 2 points. If you have 3 points not on the same line, there is exactly one plane. So if I had points E, Q, and R, okay, exactly one plane contains those 3 points. So 3 points, not on the same line, there's exactly one plane. Now, this third postulate is very similar to the first, and some people think they say the same thing, but they really don't. They're kind of converse of each other. This one says, a line contains at least 2 points. So it is saying, if you have a line, it is going to contain 2 points. How is that different than the first one? Well, the first one says, if you have 2 points, you can draw a line between them. The third one says, if there is a line, it's going to contain 2 points. Do you see the difference? David? Oh, yeah. Yes, you could have infinite points. And then the fourth one is very similar to the second one as well. It says a plane contains at least 3 points not on the same line. So this one starts out with the fact that you have a plane, okay? And it says that you're going to have 3 non-collinear points on it. The second one says that if you have 3 non-collinear points, there's going to be exactly one plane. This one says if you have a plane, it's going to contain at least 3 non-collinear points. So like I said, they're kind of converse of each other there. All right. The next one says that if 2 points lie in a plane, then the entire line containing those points lies in that plane. All right. So you have a plane, and it's got 2 points. We'll call them A and B. It says if 2 points lie in a plane, then the entire line containing those points lies in that plane. So if I draw a line between those 2 points, not only do the points lie in the plane, but so does the line. Now these next 2 we've talked about, we just didn't state them as postulates. And it says if 2 lines intersect, their intersection is exactly 1 point. So here's line L, here's line M, and if 2 lines intersect, their intersection is a point. And then the last one says that if 2 planes intersect, their intersection is a line. And again, we talked about that like in one of the first lessons that we covered, and I'm not drawing this one. But if you have a plane, and it's intersected with another plane, then their intersection is a line. Okay, so if 2 planes intersect, their intersection is a line. What we're going to do with these postulates is I'm going to give you some statements that you're going to determine whether they're always, sometimes, or never true. And you're going to use these postulates to back up some of these statements. Now, when you use one of these postulates to back up one of these statements, you cannot identify it by its postulate number. Everybody hear me on that. Okay? I have no idea what postulate 2 says. You don't either. Okay? You won't, even if you use it, you're like, oh yeah, that's that 2-1. You won't know what it says. You need to state it, okay? And so, like I would have to state, through any 2 points, there's exactly 1 line, okay? I cannot refer to it by the postulate number. Does everybody hear me? Look at me. Can you refer to the postulate by its number? No, you may not refer to the postulate by its number. Because let's say you transfer the union, they're using a different geometry book. Okay? Their geometry book, it may be a different postulate. Okay? It's not like a universal postulate. So you need to know what the postulate says. Okay? Do what? You would have to transfer the union. Okay. Alright. So here we go. Now, the answer is sometimes you can draw a picture of both situations. If it's never or always, usually you can back it up with a postulate or a theorem or something. Okay? Alright, so let's look at the first one. It says, if points A, B, and C lie in the point M, they are collinear. Sometimes, always, or never true. It would be sometimes. You're right. Okay? And we can show both situations. Okay? They could be collinear. There's A, B, and C. So they could be collinear, or not. And they called it plane M, so I'm going to call it plane M. Okay? So that one would be sometimes. I can show both situations. There's exactly one plane that contains non-collinear points P, Q, and R. There's exactly one plane that contains non-collinear points P, Q, and R. Sometimes, always, or never true. Think sometimes? If there's any 3 points not on the same line, there's exactly one plane. So what would that be? That would be always. Even if there's not a plane drawn, you could have 2 points on one, and you could have this other one here, up in space. I could still draw a plane between those 3 points, even if you can't see. It's kind of like making, running through the plane of on a football game. When you make the touchdown, you break that plane. You can't really see it, but it's there. Okay. So this one would be always, and we would write it out through any 3 points not on the same line. Here is exactly one plane. Three points not on the same line. There's exactly one plane. Alright, how about this one? There are at least 2 lines through points M and N. There are at least 2 lines through points M and N. Some of you are shaking your head. Never. Why is that? What's it say? Very good. For any 2 points, there is exactly one line. For any 2 points, there's exactly one line. Now this next one you might have to think about a little bit. And sometimes you might have to put 2 postulates together. 2 lines determine a plane. 2 lines determine a plane. You think sometimes? You may think always? You think always? Let's draw a picture. Okay? And that might help us determine. If I have 2 lines, I can have 2 lines that were parallel, right? Or I could have 2 lines that intersect, correct? Either way, because they're lines, they're going to contain 2 points, yes? We'll call this A and B. And B, and this one C and D, okay? If they intersected a point, right? So we can say this was A, this was B, and let's say this one was C. So in either situation, do I have 3 non-collinear points? I do in both situations, don't I? Either one of these, I have 3 nonlinear points, don't I? So, and what do 3 nonlinear points determine? A plane. Okay. So, your line contains a line contains at least 2 points, and through any 3 nonlinear points, there is a plane. So, this would be always. So, line contains all right, we got that. Okay, now, we are going to start talking about proofs this week, okay? And how many of you like to argue? My youngest son loves to argue, so does my middle son, okay? Does it irritate you when you're talking, like maybe arguing with your parents, and their reason is because I said so? It makes you really mad, doesn't it? Okay? But let's say you disagree with what they're saying, but if they explain it to you logically to where it makes sense, it's a little easier to take, yes? Yeah. Other than just, I mean, sometimes you still don't like it, but it's a little bit easier to take. Okay. And so a proof is a logical argument in which each statement you make is supported by a statement that is accepted as true. So if they say, you can't do this because, and it's a good logical reason, and then you can't do this because, and you can't do this because, and if the reasons are relatively good for your safety or whatever, it's easier to understand, okay? And so that's what we do. We have 2 types of proofs. We have a paragraph proof, which is a more informal proof, and we have a 2-comma proof, which is a more formal proof. And we are primarily going to do the 2-comma. But today I'm going to show you what a paragraph proof looks like. But in the proof process, you are given information. You list it. What are you given? What is gospel that you know to be true? Okay? Draw a diagram. Illustrate the information. A lot of times they'll give you a picture. You can get information from the picture. Okay? They also give you what you want to prove. And so what your job is to start with what you're given and make a series of logical statements backing them up with reason until you come up with what you're trying to prove. Now, when you create those logical chain of events, it's kind of like telling a story, you have to justify everything with a reason. And when you justify it with a reason, your reason is usually a definition, it's a postulate, it's a theorem, it's a property that you're going to learn. And so you continue in that logical chain of events until you come up with what you're trying to prove. Kind of like Chetney in the Legally Blonde video, right? She realized that she had a perm, and she made the connection that if you get a perm and you wash it, you don't wash your hair, and blah, 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 blah. You know, went through the whole thing today. All right. So this is a paragraph proof. Okay, David, are you getting all this? Okay. This is a paragraph proof, and it's given that M is the midpoint of AB. Write a paragraph proof to show that AM is congruent to MB. All right. And this one doesn't give you a picture, so I'm going to draw a picture of the M. Okay. And M is the midpoint of AB. And we talked about midpoint in the last chapter. What does it mean for something to be a midpoint? It's right in the middle, which breaks it into 2 equal parts, okay? The definition of midpoint says that it breaks our statement into 2 equal parts. But instead of using equal, I want to show that they're congruent. We also learned in that last chapter that if 2 things are equal, they're also congruent, right? And the definition of congruent segments allows us to go from equality to congruence and vice versa, okay? So that's what I'm going to use to come up with my paragraph proof. And I'm just going to do a series of if-thens, okay? So, and I'm going to back it up the reason. If M is the midpoint of AB, Well, if M is the midpoint of AB, then AM equals MB. Okay, well, if AM equals MB, then what does the definition of congruent segments tell us? If AM equals MB, then we can say that they're congruent, right? Okay? So then AM is congruent to MB by the definition of congruent segments. And so there's my proof. Two if-then statements in that case. I started out with M being the midpoint. From that, I deducted that AM equals MB by the definition of midpoint. And if two segments are equal to each other, then by the definition of congruent segments, I can say that they're congruent. So what I've done here is I have proved my first theorem, called the midpoint theorem. And the midpoint theorem says that if M is the midpoint of AB, then AM is congruent to MB. So we learned about the midpoint definition, right? And the definition of midpoint says that the two segments are equal, their measures are equal. But the midpoint theorem tells us that if M is the midpoint of AB, those segments are congruent. Okay? So, if you're going to state equality, you use the definition. If you're going to state congruence, then you use the midpoint theorem. Now, what's it matter? Well, it does matter. Because in order to do addition, subtraction, multiplication, division, you have to be in the equality mode. Okay? Which we're going to talk more about in the next couple days. If you can't add, subtract, multiply, and divide in the congruence mode, but there's other properties that deal with congruence, and there's properties that deal with equality, and then they share some properties, and we're going to talk about that this week. Okay? So, that is that little paragraph proof. Now, you probably won't even have to do one today. I'm just kind of showing you what one is. We're going to baby step our way into all this, all right? We're not going to do that last proof at the bottom because it assumes that you know information that we're going to cover tomorrow or the next day. So I'm just not going to do those last ones, okay? All right, now, if you look with me on page 130, I want to show you something real quick. Okay, on page 130, on the problems like 1 through 6, okay, let's look at number 1. I know you don't have to get number 1, but let's look at it. Well, let's read the directions first. It says, explain how the figure illustrates that each statement is true. Then state the postulate that can be used to show each statement is true. Now, the first part I think is redundant because you can look at the picture. The question says planes P and Q intersect in line R. So you go over here and you see plane P and you see plane Q, right? Well, obviously they intersect in R. You can see that's where their intersection is. Okay? What I want you to do is just to state the postulate that supports that. Okay? So what was the postulate? If two planes intersect, their intersection is a line. And so that's what you would have to do. Now, can I say postulate 2.6 or 2.7? No. No. You have to actually state it out. Okay? Okay? All right. Your assignment is on 4.